For now. I'm assuming Cody will show up in about 2 minutes if he comes.
Perfect.
Why not play the guitar?
You can do a lot more when you have full setup.
Anyway, today's lecture is going to be a little bit on the shorter side. So for the RL circuit, so we're now going to look at the resistor inductor circuit to go through. And today we're going to be looking at it in series. On Thursday, we'll look at the parallel combinations thing again. You do have a test on Friday. It does not have RL circuit stuff on it beyond what we've already talked about. So when we introduced the inductor and we had the time constant tau, and we had the increasing and decreasing current, that stuff is fair game. But the stuff we are talking about today will not be on the exam. So last time when we talked about the parallel circuit, we had a bunch of different equations that came from it. So our definition for Z, or our impedance, looks a little bit different between series and parallel. And then we also had the inverse values of everything. Let's see. So with this here, right, we have our G. This is the inverse of resistance. We have BC, which we'll see BL on Thursday. Right, that is the flipped over value of reactance for the capacitor. And then we had Y, which is the impedance, being the inverse of our Z value. And so with all of these here, again, technically with G, B, C, and Y, they are optional to go through and use. You do not need to use them to solve. It just might make your math a little bit easier to go through and do. But again, if you don't feel like using it, you don't have to. And then we talked about combination RC circuits. So with that, if we have some series parallels, some series stuff, and some parallel stuff, how do we go through and start combining those? As we saw in the example, we have to flip back and forth between right, polar and rectangular form, depending on if we're adding and subtracting versus multiplying and dividing. You'll see that again on Thursday, but this time for the RL circuit. So we'll be hitting a lot of the same topics this week as last week, but these are now all going to be the inductor versions of the circuits. So the equations will look different. But any questions from last time? Today we're going to look at the sinusoidal response of a series RL circuit. So again, with doing these, we'll just be looking at AC sources, the impedance equation, and then some things to analyze it. I don't have your packet. I probably will not have your packet this week for the stuff, so you'll probably get it next week when we start the RLC circuit. So here we have our simple series RL circuit. So we have a single resistor in this case and a single inductor. And with these here, they are in series with each other, and they happen to be in series with an alternating voltage source. So here we have, it's nice little sine wave, and we want to go through and look at for the resistor, inductor, or the resistor and the inductor, what are the voltages across those? So for the resistor, it is now going to lag behind the source. So with the RC situation, we had a similar looking circuit. We saw in that case the resistor voltage led the source. Here it's going to lag. For the voltage of the inductor, it is going to lead the source. So when we go through and look at this, we're going to see that there are some ideal situations that we can talk about, but in reality, because we're going to have this resistor inside of here, it is not going to be by 90 degrees. So the 90-degree value that you that we talked about before for the difference between the source and the inductor, that is only if we just have the inductor. Now that we have an inductor and a resistor, there's going to be some variance in how that's done. And so for that, we need to figure out what inverse tangent we're going to be using this time. But the value will be between 0 and 90 degrees. So here we have our two voltages. Now our resistor is the lagging object and the inductor is the leading object. And we will now also have that the current is going to lag the voltage source. So again, if we think about what an inductor is doing, because we have a constantly changing source, that means that the inductor is constantly creating its own induced voltage and thus an induced current. And that is going to be counteracting that change that we have. So this is why the behaviors are going to be different. So what it's doing versus what the capacitor did are, I want to say they're opposite, but they do have pretty, the effects of the circuit are very different compared to each other. Any questions so far? So because we have the voltage is leading from the inductor, it is going to be positive JXL. Where again, our definition of XL is 2 pi times the frequency times the inductance value. So with this here, again, with the notation that the textbook is going to use, is the bold here is kind of its vector representation. So this is purely an imaginary value if we're if we're thinking about that polar right. So with the capacitor, it was negative JXC. For the inductor, it is going to be positive JXL. So when we have the two in series, our equation looks similar, but now instead of a negative sign, it's a positive, and it's XL instead of XC. So this is kind of showing, right? We saw it a little bit when we first introduced our reactance values, right? With having the XC and the XL. It can help make stuff nice because now we have similar looking equations for capacitors and inductors. The same thing was true with why we wanted to use tau instead of using RC and L over R for those, right? We want to be able to again, they're not the same equations, but format them in similar ways because it helps us start comparing them a little bit nicer. It also is going to then build up into the RLC circuit where we're going to have resistors, capacitors, and inductors all at once. And so if we have everything in terms of ohms, which is why we have XC and XL, we're going to be able to go through and similar to what we did with combining parallel and series RC circuits, we can do RL circuits, and then we can do RLC circuits as well. That is the inductance value or total inductance, depending on the circuit. So with it here, again, with this particular representation of the impedance, the phasor representation looks like this. So our reactance, or sorry, our resistance is along the real direction, whereas our information for the inductor is along the positive imaginary axis. So that's why, again, it's positive J for an inductor. And once again, we can go through and use trig to help us go through and find what is the magnitude of our impedance as well as its angle. So the magnitude equation, same that we had before, x squared, now it's xl squared. And then for our angle, it's the inverse tangent of xl over r. So again, because of how this is set up, that is going to put us in the first quadrant, which means that our angle is between 90 and 0 degrees. So again, when we are representing our polar form, we will still need to go through and indicate if it is in degrees, or if, right, if our calculator is in degrees, answer pops out in degrees. If it's going to be in, if you do it in radians, you should somehow indicate that it is in radians. So again, that would be unitless, or put rad for radians. Any questions so far? So let's do some examples. So this is 4A here. So we want to determine the impedance, magnitude, and phase angle, and we want to draw the impedance diagrams. So I want you to go through and figure out how, right, find your Z and theta values, and then give it a shot on drawing that impedance diagram. And feel free to discuss with your neighbors as you work on that.
It seems like you're doing very yeah. Just remember, it's just the square root of those squares. And what you do is am I right? No, we didn't have to do any parallel because we redefine everything to. This, this over. Thumbs. It's always there. Okay. So, but when you spend, just. Right, so, sorry, it's just like one. Yes. Um. So that's. Yeah. Brain cell second. Hearing what you've been saying, yeah. So that's it. Oh, it's just that's wrong too. It's better.
It's, do you have it in rectangular or do you have it with the magnitude and the angle? So
So what is it? What is the physical?
it's just a representation.
Like if you read that the impedance sees some number. Then.
Then it's probably given as this.
Oh,
For
so
your
the magnitude is gonna be the actual like ohms.
Yes. So this is an ohms.
Okay.
And then, so technically both of these components here are in ohms as well. But
But that's,
this is if you care about the different components, you would do it this way. If you care about the circuit as a whole.
yeah,
This
So
is
you're
the
just
more
like-
important.
figure out how much, like, how much impedance is there, you do the magnitude of the impedance,
Typically,
like, to get like the actual value of the ohms.
Yeah.
Okay.
this is typically what you would want to do. But, right, depending on what you're gonna be doing with it, you might need it to be in rectangular. You're adding multiple impedances together. So, it's an awkward play of going back and forth between them. Does anybody want more time for number 4 here? All right, what's the first thing we should do before we go to try to solve for the impedance values?
Figure out the resistance.
Resistivity?
Something along those lines.
We don't want to,
Resistance.
well, resistivity is a material property, which we don't care about in this class.
The actual word.
Okay, so that's going to be XL is equal to 2 pi FL. What would I use for L here?
150 million.
So it should be the total value. And so just because these are in series, similar to resistors, we just add the values together. So we're going to have 50 millihenry plus 100 millihenry, so 150 millihenry. Do we need to convert it before we put it into our equation here?
The 0 point. Oh. Technically, yes.
I mean, that's converting it. Right, so we, in this case, because our frequency is given in hertz, we need to make sure that our inductance value is given in Henry. So we're going to be able to go through and do that. So we'll have 2 pi, 100 hertz, 0.15 Henry. Taking that in, plugging it in. I didn't want to drag around decimal points doing this at this time, so I just left it as 30 pi. you are more than welcome to go through and plug in the pi values if you want to. What's the next thing we should probably go through and do before we get to Z?
Get to see.
Yeah, that's what I'm looking for. I want impedance, that's Z. Yep, so these are in series here, so how do I find the total value? Yep. 56 ohms plus 10 ohms, 66 ohms. We now actually can go through and draw the impedance diagram or start drawing it if we want to. So along our traditionally x-axis, we could go through and we can draw in that total value. Let me draw that a little bit longer. We'll have RT here. And we also can go through and plug in the XL value. That should be here. So this is 30 pi or 94.2. If you're familiar with different adding methods for vectors, you could finish the diagram now, or you could go through, do the math, and then draw the impedance on here. Both methods are fine for doing this. So let's go ahead and let's just do the math for it. So for impedance for series, it's going to be the same for both capacitors and for inductors with resistors. So it's going to be R squared plus XL squared. So we can just drag those numbers into here, going through and plugging that in. I got, I think I put my decimal point, 177.25 ohms. And draw a decimal point, so I'm hoping that that seems to me mentally correct where that should go. Is that what you guys got? Yeah. I mean, I could be really off as well. I was trying to rush through this. Okay.
15.2.
Okay, I probably just forgot something that's totally possible. So that is going to be the magnitude value. We need, before we just go through and draw this willy-nilly onto our impedance diagram, we do need to have the angle. So if we're going through and doing that, it's the inverse tangent of XL over R. So with going through and doing this again, so I'll plug in my 0.15, sorry, not my 30 pi divided by R, so my 66. When I did this one I'm a little bit more confident in. I got 54.997 degrees.
Yeah, 55.
We haven't rounded yet. What if we needed this for part B? We don't. But, good practice to have it there. That means that Z is going to be equal to 115 at 54.5 degrees ohms. Yeah, so this is typically, if you look at how it's done here, this is how this textbook can represent it. You'll put your Z value, the angle symbol, instead of saying like theta equals, and then you'll just put your direction. This is typically how you see it done for, from what I've seen of electrical engineering, this is how it's represented. if you look at other places where you're using trig to do this, you will put the value comma theta equals to do it. So we can now go through and draw this in. Something maybe not so 45-ish, something like this. So we can put 55 degrees here and 115 here. Yes. So I guess we could put 66 here instead of RT. Yeah, everything here in an impedance diagram is always going to be in ohms. So sometimes you'll see them written in, sometimes you won't. It all just kind of depends on that. If you want it to be the most complete, you'd put ohms everywhere. Any questions about 4A? So how is 4B going to be any different?
I mean, it's really not, because we can just redefine the circuit because we know these are in parallel, so we can get a equivalent inductor and then just treat it like we have it in the series.
Yeah, so I mean, we're doing the same steps, it's just how we do LT is going to be different. So how do we do LT when they are in parallel?
Same as resistors.
That's not what I'd asked. Okay, so what is it for resistors then?
Plus.
Yeah. So 1/5 plus 1/8 inverse. Right, so this one, unfortunately, not a nice number to go through and drag around. You have the option, in this case here, based off of our frequency, do I need to convert? In this case, I don't technically need to because I have kilo, so 10 to the positive 3. I have milli negative 3, so the conversion's going to cancel out. I don't have to. You can. I don't think it hurts. But right, for going through and doing this, I got 3.07692 millihenries. And now I'm going to go through and I'm going to do the same steps as last time. So I'm going to find XL. That's going to be 2 pi. This time I'm going to have 20 kilohertz times, I don't want to write this number again, so I'm just going to draw a little arrow here. That got me 386.658 ohms. Do I need to find an RT value?
It's already there.
Yeah, so in this case, RT is equal to R, which is 560 ohms. I don't have to do anything to it. It's just fine as it is. So for Z, I'm going to have those values squared. Taking this and plugging it in, I got 680.5175 ohms. And for my angle value, right, in this case, bless you, right, it's XL, so the 386.658 over 560. I got 34.6236 degrees. So again, I should go through, I should make my answer look a little fancy. So I'll have Z equals 681, 34.6 degrees. Yeah. Yeah, that's the other, so Yeah, we could do 681 ohms, 34.6 degrees. Both are fine. Typically, if you see the ohms on the outside, there's parentheses involved just to indicate that it's not an angle somehow measured in ohms or degree ohms or whatever. So as long as it's somewhere, that's fine. So again, we should go through here and draw our diagram. So here we'll have the XL value to 387. This time, let's put the ohm symbols on it just to see what it looks like. For the resistor part over here, 560 ohms. And then combining the two of them, not to scale, 34.6 degrees, 681 ohms. So, let's say hypothetically you get asked to draw an impedance diagram. As long as stuff is pointing roughly in the correct direction, I will be content. Again, I'm not going to sit here with a protractor, dock you if you're at the wrong angle.
Even if we put on the scale.
Even if you don't put not to scale, I'm not going to sit there and get a protractor, slap it on my computer screen, especially since somebody in this class, sometimes their pages are sideways. And so I'll have to rotate it. And as it rotates it around, it moves everything and it's annoying. I'd rather just not deal with it. So, right, because you would probably never plot this by hand in your field. So I'm okay not making you do it for points or for accuracy points. Any questions on number 4 here, A, B, or anything we've talked about up until this point? Again, we're seeing a lot of similarities by having this right? Our impedance equations look similar because we have the reactance values. Ohm's law looks exactly the same for both RC and RL circuits. Just that definition for Z is a little bit different. So nothing exciting there. But let's go through and let's talk about the relationships between current and voltage. So with this one here, we have the voltage for the resistor and the inductor on here. And we also have the current that is flowing through the source or from the source. So that I there is the current that is in our circuit. What do we notice? Because they're in series, right? They should have the same current. That was one of the first things we talked about in this class. That still holds true. So what do we notice about the phase between the current and the voltage across the resistor? Are said to be in phase with each other. So there's no phase difference between them. What about for the inductor?
Hit by 90 degrees.
Yeah, so it's ahead by that 90 degrees, so it's still leading by that value. So, yeah, right, again, that 90 degrees is showing up. That does not mean it's 90 degrees with the voltage source. It's 90 degrees to the resistor voltage. So now that we have our resistors and the inductors in a circuit together, the voltage across the resistor is not going to be in phase necessarily with the voltage from the source because of that inductor and how that inductor is going to behave. So 90-degree phase difference between the resistor voltage and the inductor voltage, where the voltage from the inductor leads by 90 degrees, which is why it is a positive cosine instead of a negative cosine. Again, that's showing up in our equation for the inductance where it's positive J instead of negative J that we had for the capacitor. So with this, we are going to have a couple of different equations in comparison to the capacitor. So again, right, we're still using the, right, we'll have XC versus XL. That's not the only difference that we're going to have. So here again, positive J. So here for our source voltage, it's going to be equal to the sum of the resistor voltage plus the imaginary component, which is the voltage across the inductor. So this here is the rectangular form. You can go through and do this in polar as well. So still going through using trig to go through and define that. So we'll have Pythagorean's theorem to find the magnitude of the source voltage, and we will have the inverse tangent to tell us the angle value, where that angle is the phase angle between the resistor voltage and the source voltage. So when we go through and find this theta, that is between the voltage source and the resistor. We can then by default go through and find the value for the inductor because that is a 90-degree difference from the resistor. So with this number here, it's going to explicitly pop out the resistor difference, but we can mathematically solve for right, the inductor one if we need to. Any questions so far? So with the increasing frequency of our source, we saw for the capacitor that the reactance would get small, or the impedance gets smaller because the reactance gets smaller. For the inductor, it's the exact opposite. So as we increase the frequency, we are increasing the X value, because if we look at our equation here, as frequency goes up, multiplying by larger and larger numbers, XL has to be larger. By default, that is going to mean the impedance gets larger as well. So again, with the capacitor and the inductor, we have very different behaviors happening in the two of them. That's why we keep getting these differences in signs between them as we go through and look at our definitions of equations. Any questions before we do an example? So we need to determine the magnitude and phase angle of the source voltage. I want you guys to discuss how would we go through and do that with your neighbors.
angle. Vectors bring the information to the resistor, the current, but not the voltage. So you're close.
Right, no, I just want to, so we'll know that we can change it all to rectangle. Yeah. So.
Does anybody want more time for 16? So based off of the image, how should I go through and write out my voltage values for L1, L2, R1, and R2 first? Sorry, I'm just trying to put the voltages in here really quick.
So take one of those.
Why do we know it's 0 degrees?
Shown what else?
Yeah, so R2 is given at 0 degrees. And because they're in series, they should have the same phase for their voltage. So that's how we're going to be able to do that. 2 volts, 0 degrees. So if instead you had been given 15 degrees for your resistance, or for R2, all of them, all resistors in series would need to be that 15 degrees. In that situation, what would the angle be for the inductors? Yeah, so you just 90 plus, whatever. Yeah.
105.
Yeah. Yeah. right? You just take the value for the resistors, add the 90. So do I want to use these to help me solve for the voltage, magnitude, and phase angle for the source? Probably not the best method. Because at the end of the day, according to Kirchhoff's voltage law, Vs is going to be equal to VL1 plus VL2 plus VR1 plus VR2. So because we're going to be adding all these voltages together, the best way to go through and do this is to convert them into polar form, which in this particular instance isn't bad. So if we're going through and doing those for the resistors, are they in the real or imaginary direction?
Real.
Okay, so we'll just have 6.9 and 2. That means the inductor should be in the imaginary one, positive or negative. So it's positive 90 degrees, positive J. So we'll have plus J15 and plus J 8.5. Now that we have those, technically we can go down and plug them into the equation here. So we'll have J15 plus J 8.5 plus 6.9 plus 2. And with this, we can only add the J terms to each other. We cannot add the 2 to either of the J terms, so we'll just add those two. Add the J values, so we'll have 8.9 plus J of 23.5. So this is the rectangular form. This is not what we are being asked to solve for. We want the magnitude and the phase angle. So what do I need to do from here?
Square both of them and square
Oops.
root.
Yep.
You get the magnitude. And then arctangent J over real.
So we'll have this here. When I went through and plugged this in, I got 25.129 volts for my theta value. Inverse tangent of 23.5 over 8.9. That got me 69.257 degrees. I should go through and round these and make it nice. So we'll have Vs is equal to 25.1 volts at 29.3 degrees. Oh, sorry. I don't know why I said 29. Yeah, 69.3 degrees. So again, a lot of the same rules that we saw for RC apply here. The equations look different. Right, so for the capacitor, right, it would be 90 degrees, negative 90 degrees instead of positive. So we'd have minus J. That would also mean that our angle is going to pop out as in that fourth quadrant. So just please be careful of when you're dealing. So again, for the exam, it's just going to be capacitors. But for the final exam, you can have both. And when we look at RLC circuits, we'll have both as well. We need to keep track of what signs correspond to what. Any questions on 16 or any of the stuff we have talked about today? All right, so that's all I have planned. So yeah, so tomorrow we're just going to be finishing the packets. I still need to finish those solutions. They should go up before class tomorrow at 2. Again, on Thursday, it's going to be a little bit short just because we've seen a lot of this stuff. It's now just applied to L instead, so it's a lot of just flipping some letters around. But yeah, if you have any questions about the exam or anything, feel free to stick around and ask.
Is